Concerning the bias, the applied bias, it could be, voltage bias. It could be very useful not only to improve the measurement of the multi-junction solar cell. Also, if you want to try to measure the single junction solar cell, the variation of the applied bias could be very interesting, because actually in the most cases of the measurement, especially for single junction solar cells, the quantum efficiency is measured at short circuit current. And people assume that spectral response doesn't depend on applied bias. In sometimes it's, I would say in some range, it's a real case. But for several junctions, especially for p-ion junction, and based on defective materials like amorphous hydrogenated silicon or CGS, it's not really the case. The reason that, there is some indication. You have a two-band diagram which are at positive voltage and a negative voltage. So you see, when you apply some negative voltage, you increase the field in the undoped region, and by increasing the field, you actually decrease the recombination, because if there is no field here, or if the field is less, there is no field, also the charge carriers would recombine easily, especially if you have a lot of defects in this region. And by applying this field, you can separate the carriers and suppress the recombination. So actually, it's the main idea of p-ion structures. Why do we use p-ion structures? I would say, if we use p-ion junction, it means that there is some problem with this material. Problem. For example, there are a lot of defects, and the recombination rate is high. It's too high. It's a way to increase the efficiency, to increase the short circuit current. But if you have a low recombination rate in the volume, there is no reason to produce the p-ion junction, because p-ion junction, sorry. Because in case of p-ion junction, you would get better results, you would get better VOC value. The main reason that here you have a recombination in the space charge region. If you have a p-ion junction, you have your space charge region is smaller, and recombination in space charge region is lower. So it's a little bit another thing, but just I want to say that p-ion junction already means that you have some strong recombination losses in the material, in the volume. And the way to characterize them, to get some ideas about this recombination, is to try to measure the quantum efficiency at different voltage. So you see here there is some results of the measurement of the quantum efficiency at reverse bias. Green it's a zero bias, and blue it's some positive bias. So you see there is some decrease of the quantum efficiency due to the decrease of this field, and then we provide the high recombination losses. And if you want to really characterize the material, you can use it. So once we have measured the quantum efficiency spectrum, of any junction or subcell of multi-junction solar cell, we can calculate the value of short circuit current. So if you have a multi-junction solar cell, you have several number of junctions, you can calculate it for each junction. So it's the index G. It means that it's for the number of junction is G. And then when you have calculated this value, so you can really estimate the short circuit current of your solar cell, of the multi-junction solar cell, and you can calculate the parameters which are required for better IV curve measurements, like a spectral coefficient or the spectral mismatch coefficient M, and any other coefficients to make ideas about what kind of reference solar cell to use and what kind of solar simulator to use. So now a few words about the experimental instrumentation realization of this technique. There are different ways to realize the quantum efficiency measurements, but the main idea is that you have to use some source of a monochromatic light, and for this reason you can use is a set of the filters. If you want to make the measurements of some module or some large area, then you can use some source of light. There could be different source of light. It depends on your spectral region. And using the appropriate filter, you can select the wavelength, or actually the region of the wavelength, because filter, you see, you have always some band of the band path. But there is another important thing which is quite useful, especially for this measurement using the bias light, that to improve the signal to noise ratio and to be less sensitive to the light, you have to use the optomechanical modulator, which is called the chopper. So it's like you have some wheel with holes, which is rotating wheel. So it's just real mechanical modulation, and it is connected to synchronic detector, which is called the lock-in amplifier. So in this case, you measure really modulated signal. So it's like for the monochromatic light, it's a modulated signal, and you know that it's much more easier to measure any modulated or alternative signal compared to continuous signal, because in this case you are really more selected in terms of the noise, so you can really increase this signal to noise ratio. And the way to measure the module, for example, a thin film module, where you have junctions which are connected in series, so it's different junctions. I mean, it's a strip of one strip, it's one junction. It's not a multi-junction solar cell. I mean, it is not tandem solar cell. It's just a model with a series connection. And actually here there is approximately the same approach, because you want to select the signal from a separate junction, separate cell, because it could be just a model of the different the different design, like crystalline silicon with different wafers which are connected in series. And just if you want to get the signal from a signal wafer, the same idea. You use the monochromatic light, you illuminate by the monochromatic light the single cell or some strip or part of the multi-junction cell. So it means that there is some cell which is connected in series. And to avoid the problem that the other cells limit the current, we can use some bias light. In this case, there is no reason to play with the spectral. We can use just white light or some light which gets some current. The main idea is just to pass some current, but it's a little bit related to the idea of the multi-junction solar cell measurements. And again, if you want to measure some response of large area cells, you normally need to use intensive source of light with the filters. But if you want to measure just single cells, in this case, the more conventional way is to use monochromata. Conventional, you see, monochromata with a grating, and then approximately the same optical scheme. We have a source of light, filters just to avoid second harmonics to form monochromatic light, and local amplifier could provide some better signal to noise ratio. And of course you need because actually you need to know the number of photons, of incident photons for each wavelength. So for this reason you can use a reference detector for any case. I mean, for this with the system with a filter, or this, it doesn't. One of the main parts it's a reference detector. And so first, concerning the source of the light, if you work with monochromator, which is actually the most common way for spectral measurements, it's, quantum efficiency measurements, it's a monochromator, because normally this type of measurement is produced for just solar cells, it's not for the models. For this case, we have to think about some monotonic spectrum. It could be a xenon lamp in UV and visible light. It's not a good idea to use mercury lamp for spectral measurements. It could be used only for the system with the filters, because you see you have a set of peaks, and if you have a filter for this peak maximum, so you can get few points using this system, but only with the filters, because for monochromata it's quite hard to work with these peaks, because always need to check the reference spectrum, the measured spectrum, and it's really hard to be at the same point. I mean, the intensity, it changes quite rapidly, because actually the normal procedure, you measure, first of all, you measure the reference, so I mean, just measure the intensity, then the spectrum intensity at each wavelength. So you measure with the reference detector, then you measure the spectrum with a test solar cell. So I can produce few measurements of the different solar cells, and then again check if the spectrum is the same. There is another way to measure at each wavelength. So to change detector, so solar cell, reference cell, solar cell detector. But first of all, it's not, you have some mechanical or optical, optomechanical, so using a mirror or some mechanical system, I will show later, to move something. It's not a good idea, because you can change some I would say, if you have tips and you move always your cells, it's they could be moved also. You can get some changes. And in terms of time, it's not also so good idea, because it's much easier to set, for example, some measured solar cell. You run the program, you perform the measurement at each wavelength, because any type of this measurement is optimized using computer. Then you change the cell, or change to the reference detector, so and do it again. And so in case of this spectrum, it's really impossible to get acceptable measurements. So actually, it's why we cannot use xenon lamp in the infrared part of the spectrum. Xenon, it's here. It's this dot light, the dot line. So this is mercury, and this is the xenon. So you see, xenon lamp, it's nice for UV, and actually, I would say it's the best solution for UV light. It's a xenon lamp. But for infrared and actually the most part of the visible light, the best solution is a halogen lamp. So, and actually the halogen lamp, as I told you before, it's really easy to control. Really, so you have to just check the intensity, because you know it warms and this changing with the time. But normally, if you wait 20-30 minutes with a halogen lamp, then it's more stable. But be careful, because the intensity of the light, I would say, it depends on the temperature. And if, for example, you open the door or open the window, you can, this is different with, for example, in the winter, you can change the temperature in the room, of the measurement room, and it would affect the intensity. So it's why it's better to check again. So first of all, you know the main rule. During the measurement, don't touch anything, and it's better not open the window, don't open the door. And it's better to check if you perform, for example, 3 or 5 measurements. It depends on the time of the measurement. I mean, the time, it depends on the speed of the micrometer. It depends on the step you use. It's better to check intensity again. So normally it should not. If you start to measure with some system, first of all you have to get some ideas about what is it stable in time, etc. But in any case, it's better to check its intensity. But actually, it's always for any type of lamp. I mean, is a halogen or xenon lamp, it's temperature dependence. It's a very important thing. And there is another solution for UV. It's a deuterium lamp. It's very, I would say, it has high intensity in the UV part. Sometimes, if you really want to measure something in a region of the very low wavelength, maybe it's useful, but in the most cases, just a xenon lamp it's enough. But again, as I told you, the xenon lamp, you can choose the xenon lamp ozone free or no. In this, it depends on your task, because if you want really to increase the intensity in this UV part, so you have to select really UV lamp which generates some ozone, and you have to be careful about the safety. You have to think about the ventilation of this ozone. But for the most cases of the photovoltaic application, you should not care about this region below 300 nanometers. You see, it's not. Maybe if you are thinking about space application, in this case, but again, even for M0, this ozone region, it's not so important. Well, it depends on your task, but normally. Once I'm speaking about UV, hope you know that this 200 nanometers, actually it's the limit of the UV light you can pass in the air, because the region, the UV region below 200 nanometers, it's called the vacuum UV. Because normally, to the absorption of the air, mainly due to the absorption of the not hydrogen, due to oxygen, is too high, and there is no almost. So you have a loss of losses, a lot of losses of the intensity below. So you can go up to 180 in nitrogen atmosphere, but below it's really you need really UV. But I mean, for PV application, it doesn't matter. Just if you are interested in some spectral measurements. So concerning the photodetector, there is a quite simple solution for the most cases. It's a silicon detector, because you can find silicon detector in the range which is quite sensitive, in the range of from 200 nanometer up to 100 up to 1100, and even a little bit above. For wavelength, for high wavelength, you can think about germanium photodetector or indium gallium arsenide for detector. It works up to 1800. Normally for PV application it's enough, but then it depends. So for below it's some specific, really specific cases. It's about the choice of the material, but if you are thinking about reference detector, the main thing you have to think about, it's the detector should have some exactly known spectral response or quantum efficiency. Doesn't matter. I mean, then you can calculate the number of the photons, because the main problem of the quantum efficiency measurement that it's absolute measurements. It's not some relative measurement. You really have to perform absolute measurement, and it means that you have to know exactly the number of photons of the incident light. And to calculate the number of photons of the incident light, you have to know the spectral response of your photodetector. So for this case, there is some so-called NIST traceable term for photodetector. It means NIST, it's National Institute of Standards and Technology in the USA, but actually it means that you have a detector with a known response. It's like for reference solar cell, when you know exactly the value of the current, of the short circuit current. Here it is the same. You know for example, if you have a sensitivity, you know exactly the current at each wavelength. So, I mean, or you know exactly the quantum efficiency. It's one of the most important thing, because otherwise it's not a reference detector. So I mean, you cannot use just some detector with a typical response. I mean, it should have it-once response, which is already, this detector was measured, and the response corresponds to exactly of that detector. So it's not some typical values or something like this. Here is some examples of the setup. So approximately the same idea, but with the pictures. So we see there is a double lamp source of the light. So we can choose either xenon or halogen lamp for different range of the spectrum. Then you have here one. It's a filter wheel for monochromator, again to avoid second harmonics. And this is the chopper, so rotating wheel. So it's also rotating, but you choose some filter for several range of the wavelength. And this is, you can, by changing the speed of the rotation of the chopper, you change the frequency of the modulation. So I think it's clear. Hope that just you see there is some kind of hole, and when you rotate, you have just some modulation. You have a light, you have no light, you have a light, you have no light. So you have some modulated signal. And then using lock-in amplifier, you select this modulated signal. You neglect any constant signal from the bias light, and just this signal from an accumulator. So it's classical monochromator, and of course you have a reference, some normally it's reference detector, no, not really a cell, because there is no need to use a reference cell. But if you have a reference cell with a known spectral response, why not? So it's, and you can see here when I told about the system, rotating system. So and here, so you see it is a table with some tips to connect for electrical connection, because it's electrical measurement, so you need some electrical connection to connect to the solar cells. And so you see this table is placed on this moving plate, and you can move from measured cell and to the reference detector. And here maybe it's not really clear, but it's a different source of the light. But so I mean, you can just put something here, just near to the measured cell. There is another example of the system. The main difference I'd like to demonstrate that here there is no moving parts, I mean no moving table, but just a moving mirror. So by moving the mirror you can pass the light to the test cell or to the detector. So there is some, it's a little bit more complicated to manage with the light. You have to calculate this mirror, but the advantage that you don't care about this moving system, so just move the light. There is another solution. You can use instead of this system with mirrors, you can just now, but it depends. If you want to measure some small parts, some small cells, you can use the optical fiber. And with the optical fiber, you are really more flexible, because you can get the light into, for example, into some cryostat, so some more sophisticated system. I mean, you can combine different measurements, like a spectral measurement and IVQ, or something different temperature. Or so I mean, now with the optical fiber you are more flexible, but of course you should understand that the intensity is limited, so you cannot measure the large cell using a small fiber. So a few words about the reflectance measurements, because I told you, so the main idea, you have to measure external quantum efficiency. But if you want to measure internal quantum efficiency, you have to measure the reflectance and transmittance. So first of all, for the reflectance spectral measurements, it's a little bit more complicated compared to transmittance. That you have to use, there are different ways. So first of all, you can use optical system, for example, like this, with the rotating optical beam. When you have two well-known detectors, so there are two reference detectors with well-known spectral response, then you can either put the light to the reference detector 1, just to know what is the intensity of your light. So for example, to know intensity, you divide the current of the photodetector by the quantum efficiency. So when you divide, it comes to up, and compare with the signal from you measure it, for example, the surface of the solar cell. So you put the light on the surface of the solar cell, and measure the reflected signal. So you just calculate the difference between two, the ratio between two signals. But in this case, you have to be really careful for the light, because you know it's quite should be quite accurate with the optical system. There should be no other reflectance, so your beam should be really collimated, and etc. It's rather more complicated system. Much easier for transmittance spectrum, because actually for transmittance it's quite easy. You don't need any any calibration. You don't need any reference. So you just measure the spectrum without sample, and measure the spectrum with the sample, and then divide one. So here is a little bit more complicated system, because there are again there is a moving mirror, but you can really simplify just with, without and with, and so you get. There is another solution to make the measurements of the reflectance with optical fibers. In this case, you are a little bit more flexible concerning the management with the light. So the main idea is that you have a special fiber which include this let's say this deviation. So actually here you have a source of the light, and with one fiber it goes directly to the sample. It reflects from the sample, it goes back and goes to the spectrometer. Actually, approximately the same optical design you can construct without optical fibers, just two light which goes and reflects. And so just combine this idea with the optical fiber. But the main idea that in this case you have performed the measurement with a reference sample. So you need some reference of the reflection. It's a how to say very important point, but using this reference you should not know exactly any calibration of your photo detector or spectrometer, etc. Because actually here there are three things. So first you measure the reflected light from your sample and from the reference. Only two measurements actually. And you don't. Then you can use either optical fiber, either spectrometer, or combine anything. Because I mean, in this case, if you have some monochromatic light and measure again from the signal like this from the solar cell and from the reference surface, you don't have to know exactly the spectrum of your detector. So it's an absolute measurement, because actually reflection measurement is absolute measurement, but it is based on your reference sample. To get the reference, it's a Q point, but in this case you can simply get the ratio between two intensity. So you don't need to know exactly the spectrum of them, because it's always the one measurement system. And you have to know the reflectance of your reference, because otherwise it would not be a reference. So here, what is more specific, that instead of the monochromator, you can use a spectrometer. What does it mean, spectrometer? So it measures the spectrum in situ. I mean, using a monochromator, you can select the wavelength to measure intensity. You select the wavelength, so you have to choose always the wavelength. You cannot measure the quantum efficiency without monochromator or some source of a monochromatic light. But the reflectance and transmittance you can simply measure without monochromator, but using this type of spectrometer. Because so why it's better? Because it's quite fast. You can perform the measurement in situ. You can even in situ have some kind of mapping of the surface. So again, you have a source of the light with the optical fiber, and then actually it's not only one fiber. It's a set of fibers in around in the periphery, and one optical fiber in center. So we can collect the light. It's not all the light which comes into this fiber. I mean, it's another important thing that using reference, you don't have to think about this optical design. You don't have to think if there is some losses or no. Just a part of the light, because the main idea is that there would be the same part of the light from this sample and from this. I mean, if you keep the same distance and the equal condition, there would be the same part, and then just simply using the reference you calculate. And this, so your light come to the spectrometer, and you save the spectrum of the reference, save the spectrum of the sample, just divide them, and multiply by the reference, and you get reflectance. For transmittance, it's even more simple. So again, two measurements, but it's more simple because you don't need to have a reference. So your reference is just air. I mean, it's just a case without the sample. Again, you have some source of the light. It passes from your sample or without sample, and then it comes to the spectrometer, and you save one spectrum and then another one, and just divide the measured spectrum by the spectrum without, I mean, with the sample divided by the spectrum without the sample, and you get a transmittance. So it's quite easy. There are different things about how to get exactly the same condition with and without sample. Yes, some specific points, but the main idea it's like this. It's quite easy. And if you use a spectrometer, it becomes much more easy. I mean, the time of the measurements it's really fast. And you will see during our lab walks, because it would be for this type of measurement. And so finally, I describe this kind of measurements. It's very nice, but actually you can see from, for example, from this slide that we are speaking about the mirror reflectance. But if the surface of the solar cell is not really flat, if you have some kind of texturing, which is actually a normal case for any normal solar cell, I mean, except for the concentrated solar cell, because for concentrated solar cell normally you have just a flat surface. For this case, it's not enough to perform the measurement of of a mirror reflectance. You have to perform the measurement of the total reflectance actually, because you have a quite significant part which is related to the diffuse reflectance. So to perform it, you have to use the integrated spheres. The main idea is that the light which is reflected, so we have, for example, here I have a design of this. It's a cross section of this kind of sphere. So inside, it's covered by some material which has a high reflectance, but it's diffuse reflection. So it's like a white. You see white surface, which doesn't has any mirror reflection. And so you place this sample here. You pass the light, and then instead to the measure it's just a mirror reflection. You measure the light which out from this, and actually the idea it's you have some optical trap. Actually, to avoid any multiple reflection, because the main idea is that you should not think about this mirror reflection. You should think about the diffuse reflection. So we have a reflection in any direction, and then this light it reflects, and it comes to this output, and you have to use this kind of trap to avoid that there is some reflection like this, and oops, I mean just a diffused to be sure that you have just a diffuse reflections. Again, to perform this kind of measurements, you have actually it's the same idea. You have some reference of a diffuse reflection, and then you perform this type of calculation. Like this, it's simply, but in this case, you can measure the total reflectance. There is some modification. You can put some trap here, which capture the mirror reflection. I would say the beam of the mirror reflection. So this part of the light is captured in this trap, and it goes like this. It reflects, capture it, and it comes out. Doesn't come out, and you have only diffused part. So you can compare the diffused and total reflectance. But in this configuration, you measure the total reflectance, which is actually most important for any photovoltaic application, because you have to know the real total reflectance of your solar cell. Yes. So for this lecture, it's all.